In the last video, things were quite abstract. We introduced natural numbers using some axiomatic mathematics, some logic, some set theory, so some ground rules so that we know how we're going to proceed from now on. From here, though we're going to be doing a lot of proofs, things won't be as formal. And in fact, in this video, we're actually going to deal with a proper problem. Last video was a bit abstract, as I said, but this time we want to solve an actual problem. And we're going to be talking about linear Diophantine equations. And so to motivate these equations, I want us to consider a very real example. Say hi to Bob. Bob is an old man, and like all old men, Bob is picky, very picky. Now, you'll probably have seen a lot of mathematics puzzles with some, extravagant measures of what people want, and, Bob is one of these people. He likes extravagant things, and he's very picky about what he does. Now, Bob being old, he likes to take a warm bath to relax. But, as I said, Bob is very picky. So how does he like his bath? Well, Bob wants exactly 21 liters of water in his bath, otherwise it's not going to work. But Bob has a problem. He doesn't have measures in his bath to tell him how many liters he's filled it up to. Instead, he's got 3 jugs in his house. A jug of 4 liters, a jug of 6 liters, and a jug of 9 liters. Now the question is, can Bob actually, only using these jugs, fill up his bath to exactly 21 liters? And we don't want to be approximate here. We don't want to say, okay, this looks like about 21 liters and maybe it's, 21.2. We want exactly 21 liters. And we can assume these jugs are at exact measurements. So can Bob do this? And, if so, how does he do it? Well, to consider a problem like this, and, this is true of all problems in math, we first have to think about what the entities in the problem are actually doing. So, the bath and Bob don't actually seem to have that much importance, except for maybe the number of 21 liters in the bath. And for this problem, we can actually assume that the bath sort of has infinite volume, and that I can keep pouring and pouring and pouring into the bath, and even if I go over 21 liters, it won't overfill the bath. So how are we going to do this? How are we going to put numbers into an equation maybe that we can solve? And so let's think about that. Well, we've got our 3 jugs, right? 4-liter jug, a 6-liter jug, and a 9-liter jug. And so what can each of these jugs do? Well, all jugs, doesn't really depend on the number of what they do. All jugs can either remove water or put in water into the bath. We can either fill a jug to the max, right? So fill the 9-liter jug to 9 liters, or fill the 6-liter jug to 6 liters, or fill the 4-liter jug to 4 liters, and then pour that into the bath. And again, we can't approximate by, making 2 liters by filling the 4-liter jugs halfway or anything like that. And similarly, we can take water that's already in the bath and fill a jug with it so as to remove exactly that amount of water from the bath. So I can remove exactly 9 liters from the bath, remove exactly 6 liters from the bath, or remove exactly 4 liters from the bath. So what I can do is I can successively add or successively subtract 4 liters, 9 liters, or 6 liters to make 21 liters. So what I want to actually solve is this equation here. 4x plus 6y plus 9z is equal to 21, where x, y, z can be integers, as we saw before. Integers are all the natural numbers as well as their negation. So the reason I'm using multiplication here, right, is to embody that idea of successive addition or successive subtraction, because that really is all that multiplication is. And so the x value is going to determine how many times I want to put 4 liters into the bath. The y value is going to determine how many times I can put 6 liters into the bath. And the z value is going to determine how many times I can put 9 liters into the bath. And so maybe this isn't incredibly obvious, but if you spend some time looking at the values and trying to think how we're going to do this, you might notice that if I do 9 minus 6, I get 3, and if I add 3 to 4, I get 7. And why is that useful? Well, 21 is equal to 3 times 7. So I have a linear combination of 4, 6, and 9 that gets me 7. And now I can multiply this by 3 and get another linear combination, still of 4, 9, and 3. That gets me 21. And that's exactly what I want. Now this equation here is called a linear Diophantine equation. And linear because we're only using multiplication and addition between some coefficients that we know, 4, 6, and 9, and some unknown values. And it's Diophantine. Diophantine is named after a mathematician because we're only looking for integer solutions to this equation. We're looking for values of x, y, z that are integers. It's not the same as equations that we do in high school most of the time, which are just real equations, and we can get any real number to solve those. And so what we want to do is try and find a general way to do this process, right? Because here it was kind of just guess and find out 7 and find out that if I multiply by 3 I get 21, but that's not really useful to us in the most general sense. So in this video we're going to try to approach solving linear Diophantine equations in the general case, and we're only really going to be looking at linear Diophantine equations with 2 unknowns instead of 3. So the first step towards doing this is to note how reminiscent this is actually of division. If you think about division, all the division is asking the question of how many times does a number fit into another number. And in this case, we're doing exactly the same thing, except we're considering how many times many numbers can fit together to make some known number. In this case, how many times can we fit 9, 6, and 4 liters into 21 liters? So to address this problem, it might be natural to turn towards division and to extend even further our definitions of division that we have for natural numbers, because right now we've only looked at proper divisibility. So let's do that. So divisibility in the naturals. So again, I said that I didn't want to steer away from whole numbers, so we need to simplify division, as regular division only brings about fractions, and we don't want fractions. We want to keep whole numbers. So if you think back maybe to, I don't know if you learned this in primary or nursery, but you've probably done division with remainders. So for example, if I ask someone, maybe a child, what is 10 divided by 3? Well, he might tell me that 10 divided by 3 is equal to 3 with a remainder of 1. What does the remainder mean? It means that I take this 3 here and I multiply by 3, that gets me 9. But 9 isn't quite 10, it's 1 less than 10, so I've got a remainder of 1. That's what that 1 means here. So we want to more rigorously introduce the idea of division with a remainder, so you can stay in the whole number context. And in fact, as I said, learning about division is going to allow us to solve linear Diophantine equations with 2 unknowns by the end of this video. So, yay, excited. So, theorem 1, and we're going to keep labeling our theorems and propositions like this, is going to be division with remainder. So given an a and b that belong to the integers, right, with a bigger than 0, there exists a unique quotient remainder pair, QR, that belongs to z squared. Now, this z squared here, what that means is just that I'm taking the Cartesian product of the integers with themselves, and the Cartesian product is just a way to generate pairs like this more rigorously. So pairs means that, I've grouped them in these parentheses and I've got that comma here then. So the 2 here just means the set of all pairs of integers. If I had z to the 3, that means the set of all triplets of integers and so on. So z to the n is the set of all n tuples of integers. So that's just the notation here. Alright, so there is a unique pair QR such that b is equal to aq plus r, where r is between 0 and a, and r can be equal to 0, right? So in the case before where we had 10 and 3, well, b would be 10, a would be 3, the quotient would have been 3 as well, and r would be 1, and 1 is between 0 and a, in this case is 3, so that works. So we call QR, as I said before, quotient remainder pair for division of b by a. Q is the quotient and r is the remainder. So note how this expands on restricted proper divisibility that we looked at last time, where a divides b if and only if r is equal to 0. Because if r is equal to 0, then r is basically not here at all. I've just got b equals aq, and that's the definition of a divides b. So that's how that comes out. So let's prove theorem 1, and I mean, what is there to prove? That's it seems quite intuitive, and it doesn't actually seem like we've got any theorem to talk about. Well, we want to prove that there is such a pair, and that the pair is unique for all a, b belong to the integers with a is bigger than 0. So let's prove that. So let's take a set S. Once again, we get back into set theory, which is going to be all linear combinations of b and a, except that we only multiply b by 1. And we want these to be positive, so it's basically taking b and adding multiples of a, and we're only taking the ones that are above 0. So it should be obvious that S is not an empty set, right? If b is bigger than 0, then I can just set k to 0, and I know that b is going to be in that set. And if b is smaller than 0, then I can just keep increasing k until ak surpasses b. In this case, they're about minus ka is smaller or equal to b, and note how that's just rearranging this inequality here. So, by the well-ordering principle, S needs to have the smallest element because it's a subset of the natural numbers and it's not empty. So we call this element R, and R is going to be equal to b plus ka by the definition of the set for some unknown k that belongs to the integers. So now if we set q equal to minus k, and again we don't really know what k is, then R is going to be equal to b minus qa. And so that implies, by just rearranging the equation, that b is equal to aq plus r, or qa plus r if you prefer how I wrote it here. And so that's exactly, as required by the theorem that we wrote on the previous page. So that's that part of the proof, right? We showed that the pair exists. I mean, there is a smallest element, r, and from that determines a certain value of k, which determines a certain value of q. And it also actually shows uniqueness, right? Because there's only one smallest element, which determines a unique value for k, which determines a unique value for q. So that's already a lot of stuff done in just 3 bullet points. So now we just need to show that R is smaller than A and that it's bigger or equal to 0, because remember that was a restriction on R. Well, we know that R is bigger or equal to 0 because R is part of S. And that's in the definition of S, the elements need to be bigger or equal to 0. So that's easy. So now let's assume that R is bigger or equal to A, and we're going to get to a contradiction to show that R is actually smaller than A. Well, by plugging in the definition for R, b plus ka is bigger or equal to A, or again, the value of k, but we don't really know. And so b plus k minus 1a, which I can rewrite as b plus ka minus a, is going to be bigger or equal to 0. Now, why is that? Because b plus ka is bigger or equal to a, right? And if I rearrange this inequality by subtracting a, I get b plus ka minus a is bigger or equal to 0. So that tells us that b plus k minus 1a is bigger or equal to 0. This is just the middle step to show how we got there. So that means that b plus k minus 1a has to be an s, right? Because k minus 1 is just, another integer. That means that we know this is bigger or equal to 0, so it can be an s. But since a is bigger or equal to 0, b plus k minus 1a, which is once again b plus ka minus a, that's going to be smaller than b plus ka because I'm subtracting a value off from b plus ka, and that value is positive. And so it's smaller than r. But that means it's in S, and it's smaller than r. But r, as we said before, is the smallest element in S. So that contradicts the minimality of r. We've got a contradiction, which means that r is smaller than a, and that completes the proof. So to keep going from here, we need to start, introducing some notation, and we're going to keep doing this along the series, just to, keep things clear and uncumbersome, and so we need to try and remember the notation that we're using as we go along. So the first definition we're going to take is the divisors of b. So for some b belong to the integers, big D of b is equal to the set of all integers a such that a divides b. So all divisors of b. That's pretty easy. We're just going to denote that as db. Now, next we define common divisors. So C of a1, a2, an with all of a1, a2, an of the integers is just the intersection of all of the divisors of ai. So this symbol here, which may look a little scary, it's a big operator. It's the intersection where, it's like the sum operators where I index with I and I let it range from 1, 2, 3, 4, all the way up to n. And so that just means that I take all of the sets dai, so I take da1, I take da2, I take da3, all the way up to dan, and I take the intersection. So this intersection of sets is just another set, which is all common elements of sets. So if I take, for example, let's take 1, 5, and let's intersect that with, so intersection, it's that symbol here. Let's intersect it with 1, 4. Well, that is just going to be the set 1. Why? Because 1 is the only common element between 1, 5 and 1, 4. So that's pretty easy. So that's all that this operator here means. It's just a fancy way to write taking the intersection of all the divisors of these guys. So we're just taking all the common divisors, as the name indicates. And so we write it like this, as C of all these numbers. And finally, we define the greatest common divisor, which is just the maximal element in the common divisors. And yeah, I mean, that's all the definition we need. This max here just means the maximal element of the common divisors of a1, a2, all the way up to an. So for example, if I take 10, and I take 6, and I take 18, right? Well, this is actually not going to be very useful, but the only common divisors of these guys is 1 and 2, right? And you could almost think 3, but 3 or 6, but these don't quite divide 10. So it's going to be 1 and 2. So if I take C of these guys, actually these are not a set, sorry. Take C of these guys, it's equal to the set 1, 2, as such. And so the GCD of 10, 6, and 18 is just going to be 2 because that's the biggest element. So greatest common divisor is a really important tool. We're going to keep using it again and again and again. And we're mainly going to use it when considering only 2 values inside the GCD, because it's just very cumbersome to always use this notation of A1, A2, all the way up to AN. And if you want to try and generalize the results to n different inputs, then you generally have to do some induction. So we're only going to look at 2 variables, and some of the theorems we prove are true for n variables, some aren't. So that's up to you to decide if you want to try and prove those or not. So now we get to our second theorem, because we still haven't gotten, to something that looks like linear combinations. There's actually a really important theorem to get to that, and it's namely that if we let G be the GCD of A and B, just to make notation shorter, then there exists, that's what this backwards E means, that means that there exists some value of x0 and y0 that belongs to C, so there are numbers x0 and y0, such that G is equal to ax0 plus by0. That means I can take there is a linear combination of A and B that is equal to the GCD of A and B. So this is where we're concretely linking the concept of divisibility with the concept of linear combinations. And intuitively we could see that those were related, but now we're actually going to concretely relate them together in this lemma, or theorem. So, let's prove a theorem. Let the set of linear, L plus of A, B, be the set of linear combinations of A and B that are positive, alright? So generally speaking, we haven't formally introduced this, but this letter here, with A and B, we use it to denote the set of linear combinations of A and B, and the plus here just means that we're taking them to be positive, right? That's all that means. So we assume that A and B are not both 0, and why do we assume that? Well, if they're both 0, then the set is going to be empty. So, and also if they are both 0, then it's easy to see that the GCD of A and B is just going to be 0, right? And that's an easy linear combination. We just take x and y equals 0, and we do A times 0 plus B times 0, and that gives us 0. All right. So we can assume without loss of generality. Now what this means is generally that we can argue by something symmetric. That means if I argue for A, I could have argued for B because there's nothing discerning A and B in my thing. I could have swapped them around in my equation, it would have been the same thing. So without loss of generality, we're going to assume that A is not equal to 0. So if A is bigger than 0, then A is equal to A times 1 plus B times 0, right? And so that's going to belong to the positive linear combinations of A and B because A is bigger than 0. So then that means that the set is not empty if A is bigger than 0. If A is smaller than 0, then minus A is equal to A times minus 1 plus B times 0, and minus A is going to be bigger than 0. So that's going to belong into to the linear combinations of A and B that are positive. So it's not empty if A is smaller than 0 either. So since either we have A bigger than 0 or A smaller than 0, and remember with that loss of generality we're assuming that A is not equal to 0 because we can't have both A and B being 0, then we know that the positive linear combinations of A and B is not an empty set. So, by the well-ordering principle, we have that the positive linear combinations of A and B has the smallest element, and we're going to denote this by G, alright? And it's going to be equal to AX plus BY for some unknown X and Y. So we want to show that G is equal to the GCD of AB. And so we're going to show this in two steps. First, we're going to show that GA and GB, G divides A, sorry, and G divides B. So that means that G is an element of the common divisors of A and B. Alright? I mean, that's the first criteria to be the greatest common divisor. You have to actually be a common divisor. And then afterwards, we're going to show that G is the largest of all the common divisors. So the first step, showing that G divides A and that G divides B. So we're actually just going to show that G divides A, and it's the same as what I was saying before without loss of generality, is that if I just show that G divides A, because of the symmetry of AX plus BY, then I can show by a very similar argument that G divides B as well. So let's assume that G does not divide A, and this is going to be proved by contradiction, yet again. So then, by division with remainder theorem that we showed before, we have that A is equal to G cubed plus R, with 0 smaller than R smaller than G. Notice that in the original theorem, this here said 0 is smaller or equal to R, but here we can't have 0 being equal to R, because then that means that G divides A. So this assumption yields this change in restriction from our theorem. And we know that these numbers Q and R exist by the theorem that we proved earlier. So that implies, just by rearranging the equation, that R is equal to A minus GQ. That's a pretty easy step. And so I can plug in the definition for G that we had before, which G is equal to AX plus BY, right? So we have A minus AX plus BY times Q. And so R is equal to A times 1 minus QX, all minus B times QY. And here this is just me distributing Q across AX plus BY, then distributing this negative sign here, and then we factor things and rearrange a little. So you can do that on paper if you're not really convinced by this step. And so, well, 1 minus qx, that's an integer. Qy is an integer. So that means that this here, a times 1 minus qx minus b times qy, is a linear combination of a and b, right? So R is going to belong to the positive linear combinations of a and b. How do I know that this is positive? Well, we have here that R is bigger than 0. That's just given, right? So, but R is smaller than G. So G can't be the minimal element of the positive linear combinations of A and B, right? And we know that R is smaller than G once again by this restriction here. So that's a contradiction. And since it's a contradiction, we must have that G divides A. And so by a similar argument, as I said, we can show that G divides B. So that's the first step of the proof. Well, second step, I guess. And so now the first step is to show that G is the largest of the common divisors, and then we'll be done. So let's let G dash be another common divisor of A and B. And so G dash is an element of the common divisors of A and B. So we saw last video, and maybe you proved this, that since G dash divides A and G dash divides B, because it's a common divisor, then G dash must divide AX plus BY for all values of X and Y that are integers. That's the linearity property of proper division, and maybe you prove this or not. And so AX plus BY, right, I can take the particular value of X and Y that defines G, so that AX plus BY is equal to G, which means that G dash divides G. So since G dash and G are both bigger than 0, by the comparison property, which was another thing that I asked you to prove, we also saw last video that G dash was smaller or equal to G, because it also divides G here. So that confirms that G is the largest of the common divisors, because any other common divisor would either be equal to G or smaller than G. And that completes the proof. Now, using Bezout's lemma, that shows that the GCD is a linear combination of its inputs, we can characterize all linear combinations of A and B. And so that really gets us a whole step closer to linear Diophantine equations. So a corollary of this is that the set of all linear combinations of A and B is actually equal to the set of multiples of the greatest common divisor of A and B. So to prove this, first note that, well, the greatest common divisor of A and B, it's a common divisor, it divides A, it divides B. So that implies, again, by the linearity property, that it divides AX plus BY for all X and Y belonging to Z. This upside down A here means for all, so I take any value of X and Y, and this statement here is true. So any member of the linear combinations of A and B is going to be a multiple of the greatest common divisor, right? Because it divides all, these guys are all members of the linear combinations of A and B. So that means that they're all multiples of the greatest common divisor of A and B by this division here. So this shows that that the linear combinations of A and B is a subset of the multiples of the greatest common divisor of A and B. So, for the converse, because we've shown that this is a subset, we need to show that this set here is a subset of this set. And since they're each subsets of each other, then the sets have to be equal. That's a standard way to prove that sets are equal. So for the converse, we consider that k times GCD of A and B for some value of k, right? And by Bezout's lemma, we know that the GCD of A and B is equal to AX0 plus BY0 for some x0 and some y0. There exists an x0 and y0 such that this is true. And then I can distribute k across this addition to get A times kx0 plus B times ky0. Right? And that looks familiar. That's a linear combination of A and B. So that means that all elements of the multiples of the GCD of A and B are actually also linear combinations of A and B. So that means that this set here is a subset of this set here. And so we've shown it both ways, so that shows that the sets are equal. So note how this implies that when the GCD of A and B equals 1, then the equation C, which is equal to AX plus BY for some XY, and all C belonging to Z, is possible. I've written here implies C equals AX plus BY. This is a statement, right? And it implies that this statement is true for all values of C that belong to the integers. Now, why is that? Well, AX plus BY here, as we've just shown, is going to be equal to a multiple of the GCD. And all integers are multiples of 1. So that means that this any value of C here would be valid. It would make this equation possible, because there are equations like this that aren't necessarily solvable when the GCD of A and B is not equal to 1. So that's already one guarantee that we can give for solving linear Diophantine equations. If we know that the coefficients have a GCD of 1, then we know that the linear Diophantine equation is solvable. So this actually brings us to coprimality, and we define coprimes, or numbers that are relatively primes, as numbers A and B such that their GCD is 1. So if the GCD of A and B is 1, then A and B are said to be coprime, or relatively prime. And so thanks to Bezout's lemma, we can actually find some neat conditions related to coprimality, and that'll bring us to the last step. These are some lemmas we have to prove. That brings us to the last step to solving linear Diophantine equations. And I mean, in general, requiring numbers to be coprime ends up enabling a lot of theorems in number theory, so it's an important tool to have. So, the first lemma on coprimality, this will go. So, lemma 1. If the greatest common divisor of A and M is equal to 1, and the greatest common divisor of B and M is equal to 1, then the greatest common divisor of A times B and M is equal to 1 as well. So that's just one way to, condense these two statements into one. So, let's look at the proof. Well, the greatest common divisor of A and M being 1 means that 1 is equal to AX plus MY for some X and Y, right? And if I rearrange that equation, I have AX equals to 1 minus MY. And I've got the same thing here, and I've got X dash and Y dash for some value of X dash and Y dash. And I just rearrange to get BX dash isolated. So now I can multiply these two equations together to get A times B times X dash is equal to 1 minus MY times 1 minus MY dash. And so I can distribute that, and this is just standard distribution. 1 times 1 minus MY times 1, 1 times minus MY dash, and minus MY times minus MY dash. And so then I can factor the term of M here, which is common to all of them, to get 1 plus M times minus Y dash plus MY dash. And now if I rearrange this equation, I can just, subtract this whole term and bring it to the other side to get AB times X dash, and I've put these in parentheses, plus M times Y plus Y dash minus MY dash. Note all the signs here have been switched in comparison to here because we've subtracted it from the whole equation. And so that means, if you've noticed, that we've got AB times some number plus M times some number is equal to 1. And so this isn't true in the general case, but in the case where the GCD is equal to 1, then this does mean that the GCD is equal to 1 here, because if here I didn't have 1, and if I had another number, say 10, then this would only guarantee that 10 is a multiple of the GCD, because remember that's what we found when we characterize all linear combinations, because this is a linear combination of A, B, and M, and so that means that this is a multiple of the GCD of A, B, and M. But since here we've got 1, that means that 1 is a multiple of the GCD, and we've seen before that if a number divides 1, then that number is equal to 1 or minus 1. And the greatest common divisor can never be equal to minus 1 because it has to be positive. So that means that the GCD is equal to 1. So another lemma. If C divides AB, A times B, and the GCD of C and A is equal to 1, then C must divide B. This is an incredibly useful statement that allows us to reduce statements about divisibility to then solve more tangible ones. So, the proof. Well, the GCD of A and C is 1, as given by the lemma. So that means that AX plus CY equals 1, once again by Bezout's lemma, so we keep using that result again and again. That's where you see how useful it is. And if we multiply this equation by B, then we get B is equal to ABX plus BCY. And so we know that C divides AB, that's given here. And we know that C divides BC, because, I mean, BC is equal to B times C. So by the linearity property, C divides ABX plus BCY for these values of x and y that we have here. So that means that C divides B. And so that's exactly what we're trying to show. That's done. That was a pretty easy proof. And it's just using Bezos' lemma once again. So next, the third lemma that we want on coprimality is that if G is equal to the GCD of A and B, and you know G can be any positive number, then the GCD of A over G and B over G is equal to 1. And note that we're allowed to use these fractions here. These are going to be actual integers because we know that G is a divisor of A and of B. So we can't, this expression does mean something in the integers. But this is only because G is the greatest common divisor of A and B. Well, because it is a common divisor. So let's look at a proof for that. So let's just let the greatest common divisor of A over G and B over G be some integer k. Right? So that means because it's a common divisor, we've got k times some integer JA is equal to A over G, and similarly k times some integer JB is equal to B over G. So I can multiply these equations by G to get JA times G times K is equal to A, and similarly JB times G times K is equal to B. So that means that GK is a common divisor of A and B. We see that GK is here, and that GK is there. So if K is bigger than 1, then KG is going to be bigger than G, right? Simply by multiplying this expression by G here. But that contradicts that G is going to be the maximum of the common divisors of A and B, because G is the GCD of A and B, and that's the definition of a GCD, right? Because KG is an element of the common divisors, but it's bigger than what's supposed to be the maximum element, so that's not possible. So that means that K can't be bigger than 1, and we know that K can't be smaller than 1, because we're talking about the greatest common divisor. And 1 is always at least a common divisor, so that means that K has to be equal to 1. And so that proves that the GCD of A over G and B over G is 1. Right, so moving on. Now we can finally get to the linear Diophantine equations with 2 unknowns and solve it for the general case. And hopefully Bob can say thanks after that, even though he had 3 jugs. So let's fix an A and B that belongs to the integers. If the GCD of A and B divides C, then the equation ax plus by equals c has infinitely many solutions of this form. So just coupling things, I could have written x is equal to this and y is equal to that. So we've got x is equal to x0, and we're going to see what x0 is afterwards, plus k, where k is some integer, times b over g, and we're going to see what g is, and y is equal to y0 minus k times a over g. And so the infinitely many solutions come from the fact that k can be any integers, and we're taking multiples, we can successively add them. So, as I said, k is an integer, g is the GCD of A and B, it's just one way to make this notation more concise, and x0, y0 is a particular solution pair. So that means that I need to find 2 values for x and y that do solve this equation, and then from that I can generate infinitely many solutions. So, the last part of this theorem is that if g does not divide c, so if GCD does not divide c, then the equation does not have any solutions. So let's first prove that we don't have any solutions if G divides C. Well, it does not divide C. What we saw when characterizing linear combinations of A and B, that for any linear combination of A and B, it's equal to some J times G. It's a multiple of the GCD. So the equation ax plus by equals C requires that C is an element of the linear combinations of A and B, right? Because ax plus by is a linear combination of A and B. So that further requires that C is a multiple of G, which means that G divides C. So that part of the proof is complete. We need to have, that's a necessary condition for G to divide C. So let's then verify that the solution actually works. So let's take a particular solution, x0 and y0, and plug it into the general solution for xy. So we've got A times x0 plus k b over g, plus b times y0 minus k times a over g, this is just the format of the solution that we saw at the beginning, is equal to c. So if I distribute and I rearrange, I get a times x0, that goes to here, plus b times y0, that goes to here, and then a times k times b over g is going to be a b over g times k, and similarly here, I have got b times a over g, that's going to be a b over g. Here I've got a negative sign, here I've got a positive sign, so I've got k times ab over g minus ab over g. and that's equal to C. And so obviously AB over G minus AB over G, that's going to disappear, that's going to be equal to 0. So we've got AX0 plus BY0 plus K times 0, and K times 0 is just 0. So we've got AX0 plus BY0 equals C. And we know this is true because we were given that X0, Y0 is a particular solution pair. So this statement here is true. AX0 plus BY0 is equal to C. So that finishes the verification of our solution. And so now let's show that it's the only solution format, that any solution needs to fit that format. That's the last part of the proof. So suppose that we've got some other solution, right, x1, y1. Then by definition, ax1 plus by1 equals c. So if we subtract with a particular solution, ax0 plus by0, that defines all our solutions, this gives us, just by subtracting these two equations, we've got a times x1 minus x0, which is factored here, plus b times y1 minus y0 is equal to 0. And if I rearrange, I can subtract b times y1 minus y0 to the other side, and so that gives me b times y0 minus y1. Note that these guys have switched positions because I've subtracted this from the whole equation. And I'm just going to mark off this equation with a little star so I can re-refer to it afterwards. So I can divide by the GCD of a and b. We know we can do that division because it divides a and it divides b. So I'm just going to do that. So that means that b over g divides a over g times x1 minus x0, because this here is just some number, and so by definition of proper divisibility, we can write this as this relation. So by lemma 3, which you remember lemma 3 said that if the GCD of a and b is equal to g, then the GCD of a over g and b over g is equal to 1. So the GCD of a over g and b over g is equal to 1 by lemma 3. And so by lemma 2, which allowed us to reduce equations, relations of division, where we had some product on the other side, we've got that b over g divides x1 minus x0, because we know that a over g and b over g are coprime, and lemma 2 told us that when this was true, then b over g had to divide the other part of the product. In this case, that's x1 minus x0. So we already used two of our lemmas in our proof. So thus, that means that we need to have a k that belongs to the integers, such that k times b over g is equal to x1 minus x0, just by the definition of proper divisibility. So rearranging that equation, I get x1 is equal to x0 plus k times b over g, and that's exactly the format that we had in our theorem. So now we just need to prove the same thing for y1. So we substitute this into our equation, to our star equation that we have up here, and so that gives us a times, x1 is going to be x0 plus k times b over g, and we subtract that with x0, so that x0 here disappears, and we're only left with k times b over g, and that's equal to b times y0 minus y1. And so now if I divide the whole equation by b, I get k times a over g is equal to y0 minus y1, and now I rearrange, and I get y1 equals y0 minus k times a over g, and so we're done. That's where we finished proving the theorem. And so now we've got a way to solve every type of linear Diophantine equation with two variables. So yes, number theory actually has some uses. Now with n variables, it's going to be a little harder with n is bigger or equal to 2, and n is bigger than 2, sorry. And so we're not really going to do that. We might look later at the chicken McNugget problem, and that's the actual term. I didn't make that up. It's also more seriously called the Frobenius problem, which has to do with linear Diophantine equations with n variables, specifically when the coefficients are positive. And it's a nifty little problem that we might look at later. But first, in our next video, we're going to learn about prime numbers, and that's going to be a lot of fun. So see you then.